morning, dear colleagues and distinguished participants of this Congress. It is an honor to be here today. I'm Paula Gularte, a master's student in operation research, specializing in data science, and Dr. Vitor, a professor from the computer science division, are affiliated with the Aeronautics Institute of Technology in the Federal University of São Paulo from Brazil. Today, we are pleased to present our scientific paper, a model-based approach to scalable portfolio selection using machine learning. Presentation outline. We organized the outline of this presentation as follows. Motivations for our study, portfolio optimization through proper stock selection and allocation is one of the most recurrent issues in modern financial research, as it is desirable to generate profits in a variety of market scenarios to minimize losses during periods of recession. The Mean-Variance model has been the genesis of numerous studies that have extended its work and complements the knowledge on portfolio formation and the challenges encountered in practice, including boundary and cardinality constraints, transaction costs, and the sensitivity in estimates of expected returns and covariances. Preliminary set selections circumvent these types of constraints and reduces the computational complexity of the problem before the optimal allocation step. In related literature, recent developments in machine learning bring opportunities with clustering methods and uniform manifold approximation and projection UMAP, approach that preserve global and local data structure accurately in a shorter runtime. We know that working with financial market data is a complex problem. Would most basic cluster techniques with Euclidean distance be able to capture these complex patterns, or would other techniques with different approach be necessary? New stock allocation methodologies become popular with the 2008 crisis, such as risk parity being less sensitive to errors in parameter estimates, and hierarchical risk parity that applies graph theory and unsupervised machine learning and stands out for providing...
Dr. Anna, sorry to interrupt you, your slides are not moving. Slides are not moving.
Okay.
Yeah, okay.
Objective. The goal of this research.
It's still in my first slide. Yeah, it's still, slides are not moving. It still shows first slide only.
No?
No, not it.
Now, stop share. Share screen.
Share your full screen, then it will be enabled.
No?
No, it's not moving.
No?
Yeah, it's moving. Yeah.
Yes?
Yeah.
Okay.
Yeah, okay, thank
you. Okay.
You can continue. Yeah, thank you.
Let me see. Objective, the goal of this research is a scalable quantitative proposal via machine learning for asset selection and allocation through clustering. State-of-the-art modern portfolio theory based on introduction the mean-variance principle of portfolio return, Markowitz, 1952, established modern portfolio theory. Tobin, Sharpe, Merton, Ruiz, Turibiano, and Soares, Tu, Zhu, Brown, and Smith, Lee, Jurtzenko, Cesaroni, and Tardella, Boldnar, Prado, Wang, and Shimizu, and Shohama explore practical investment problems such as boundary and cardinality constraints, transaction costs, and the sensitive in estimates of expected return and covariances. Due to the lack of accuracy in forecasting, new methodologies such as risk parity stands out in this regard. Prado discusses the application of hierarchical risk parity with complex models such as graph theory and unsupervised machine learning. Dimensional reduction, authors Deng and Ming and Wang highlight the importance of including high quality asset in the input of portfolio optimization methods. Tayali also highlights these issues and mentions the challenges of working with many assets in the portfolio. Authors Paula, Tayali, and Tolum and Tayali suggest including preprocessing algorithms to increase the efficiency and reliability of the financial portfolio and minimize risk. McInnes, Batch, and Dorothy explore the nonlinear UMAP methods which can estimate the topology of high-dimensional data and create a low-dimensional representation, preserving local and global data structure relationship with a shorter runtime. The authors Lopes and Machado and Pellet performed numerical experiments. They confirmed the feasibility and effectiveness of UMAP in data processing in complex systems, such as the financial markets. Recent studies. These studies demonstrate that machine learning techniques in asset preselection can improve portfolio optimization and open new perspectives for finance research. Approaches for better portfolio optimization, effectiveness. PAIVA propose a model that combines asset classification with SVM in the mean-variance model to form an optimal portfolio. Tayali incorporates three cluster analysis methods into the mean-variance portfolio optimization model to preselect assets. Vang study a hybrid method that combines a recurrent neural network with the mean-variance model to optimize asset selection and portfolio formation. Gap in the literature. Only 12 of mean-variance portfolio optimization solutions in the past 20 years have used machine learning algorithms according to a comprehensive literature review by Kalaisi. Automated asset clustering methods for diversification have not yet reached an adequate level of maturity, and there is room for future developments. The K-means technique was the most widely used in the research subcategory that used machine learning algorithms. Explicit knowledge of the mean-variance model regarding performance measurements is still limited according to Marville and Tayali. Innovation in this scientific literature. This study presents a methodology distinct from previous investment studies. Dynamic methods that updates the parameters of the cluster for asset selection in each window of the investment horizon, improving the generalization capacity for new data and avoiding model overfitting. The selection of assets in each cluster maximize the objective function with consider variables measuring the financial performance and risks associated with each company to improve the risk-return relation. Results obtained in 3 allocation models are compared and validated against out-of-sample data. And innovative dynamic asset selection and parameter optimization approach to financial analysis. The data consists of 12 fundamental and 8 technical indicators calculated from the information in the company's financial statements and daily closing asset prices of companies, with historical data for 74 Ibovespa stocks and 464 stocks from the Standard & Poor's 500 index. The time chosen was from January 1st, 2016 to December 31st, 2021. That variables, they show the relationship between the position of on capital equity concerning a third-party capital loan. Liquidity variables include the relationship between balance sheet accounts. They show the company's ability to honor its commitments, especially those in the short term. Profitability variables, they show the return earned by the company on the use of its assets over a certain time. They seek to relate the company's profit to its size expressed through its sales or its assets. Risk variables for mitigate and soften impacts provides information on price volatility, measures portfolio return dispersion, and measures the maximum cumulative loss run on peak to the next bottom in the portfolio. The market variables provide information about a wide variety of large and small companies, measures the current asset price relative to earnings per asset, measures a company's market valuation relative to its book value, measures the total value of a company, and metric used as a valuation tool to compare the value of a company. Performance measures, Hirschman index, average portfolio return, annualized volatility, Sharpe ratio, maximum drawdown, and beta index. According to the literature, these portfolio performance metrics are among the most popular in portfolio management for long-term horizons. Proposed methods to ensure our data's veracity, reliability, and quality, we enlisted the assistance of Economatica. This collaboration helped us significant time handling extensive data volumes and facilitated more comprehensive analysis. Our data collection process involves directly accessing the company's data through Economatica's platform. The next stage, dimensional reduction, UMAP, worked with an algorithm that was both scalable to massive data and able to handle the diversity of data available. Dimension reduction algorithms tend to fall into two categories: those that seek to preserve the pairwise distance structure between all data sample, and those that favor preserving local distances over global distances. The next stage, we chose 3 algorithms that represent important classes of clustering. Each algorithm employs a different criterion according to the type of feature they represent. Agglomerative hierarchical cluster, k-means, and partition around midoids. We have selected the silhouette coefficient and the Davis-Baldwin index as the standout internal validation measures. The objective is to maximize the portfolio score calculated by dividing the financial metrics by the risk factors. A single score represents the portfolio's overall quality for the time t. Maximizing the portfolio score leads to a more precise selection of stocks in each cluster, and consequently a better overall portfolio performance. The resulting subset serves as input for the preselected asset allocation. We use the optimization methods, hierarchical risk parity, mean-variance, and inverse variance portfolio. The method hierarchical risk parity addresses three major concerns relative to the classical method: instability, concentration, and underperformance. To test the stability of the in-sample and out-of-sample optimization, we performed Monte Carlo simulation, generating synthetic returns from the covariance matrix and using the multivariate normal distribution. Results: first stage analysis, asset selection. Results presented in table indicate that when applied without preprocessing, k-means fail to accurately identify the cluster with only 1% of the data belonging to the second group. However, preprocessing with UMAP enable us to identify the cluster well distributedly. The figures show the results of the three clustering methods for the last quarter of 2021, and the number of cluster for k equals 5, the cluster number obtained by maximizing the split coefficient and minimizing the Davis-Baldwin index. The figure shows the average quarterly cardinality of the portfolios, which show high dispersion of results due to the varying performance of assets in each quarter, and consequently different results in UMAP. Managing a few assets is more realistic for individual investors. Our solution resulted in a financial portfolio of 80 stocks, significantly reduction the problem's computational complexity. Portfolio allocation in table, we summarize these analyzed indicators, inverse variance portfolio and hierarchical risk parity were the methods that most evenly distribute the weights among the assets, showing a moderate concentration, a Herfindahl-Hirschman index of 16, 39, and 1710, respectively. In the graph, the three portfolios outperformed the S&P 500 and Ibovespa regarding the accumulated return. In the table, as noted in the performance indicators, reflection the accumulated return and volatilities, the inverse variance portfolio had the best Sharpe ratio, 1.14, followed by hierarchical risk parity, 1.11, and mean variance, 1.01. Comparison with out-of-sample data, the results show that the hierarchical risk parity performance was superior, since the variance distribution generated by the methods suggests a more robust approach for portfolio optimization, as it can generate more consistent and stable results. Final considerations, the methodology is flexible and scalable and allows for multiple variations. The source code of our framework, database, and experiments are publicly available at GitHub. Implementing the solution with other classical dimensionality reduction techniques, such as PCA and TSNE, comparing the methods and electing the best one for the second stage of the selection. Variation in cluster formation, explore other alternative similarity measures. Some reference. Okay, thank you. Thank you all very much for your attention.